Just real quick, sharing my screen in a second. So, oh, Jafang was predicting what he was predicting. He was predicting the most laggy lecture in the universe, but maybe you never know.
Interesting. Going well so
Yeah,
far.
yeah, maybe my internet will be just fine today. Just maybe reshare real quick. Okay, you see my slides? Scalability, right? Okay, so last time we talked about the problem of scalability and synchronization, right? So essentially, uh, like we talked about memory subsystem, so we understood how the cache coherence thing works, right? So remember, we said that uh, just like on this slide, we said when we something wants to load like read something from an address which sits here in memory, right? What happens is that the cache coherence works in a manner in such that this line is brought into the caching hierarchy of this core in either shared or maybe possible with some optimizations in some exclusive state. If it's read, for example, here as well, if you do a load here on this core, then this cache line somehow like bounce here, and then it's definitely in two shared states, which means that these two cores can do subsequent loads, right? But if you, for example, try to do something like a store here, then the store instruction looks at the state of this cache line and says, okay, you're in a shared state. It cannot really be modified because someone is concurrently reading you, right? And so the way the cache works, it essentially sends something what is called request for ownership message, and essentially this cache line gets invalidated here, so it's no longer in this core, but this guy gets it in the exclusive state, right? And essentially, it's not very important today to understand how this protocol works because it's part of the standard architecture class. So Rajiv has a series of good lectures. Actually, I should probably link them on the website. So if you want to understand how cache coherence works, at least have some idea, just watch some of his lectures and you'll be just fine, right? But the main level observation which I wanted to make in this last week's lecture is that those cache lines are kind of bounds between the cores, right? And if this core wants to write a cache line, essentially it will send a message to the last level cache, which is responsible for this cache line. This last level cache will maintain something what is called a directory, and the directory essentially records all the cores. Like let's assume this is core 0, this is core 1. It will know that this cache line exists on core 0, core 1. It will send invalidation messages to them and then reply with a cache line in the exclusive state, for example, or let's say this core is number 2, and if this one is number 3, and it will essentially record the fact that 2 owns the cache line right now, and it will remember the state, right? And so this is how it works, right? And okay, so and then we went forward and we said, okay, we understand how spin locks work, right? And um, essentially, a most trivial implementation of a spin lock is just this atomic exchange instruction, which takes a data structure with a field, and essentially the exchange instruction writes 1 into that field and returns the old value saved in the lock, right? And so if it returns 0, then you're done and you just continue into the critical section. If, however, you return 1 here because someone already locked this cache line, you continue spinning, trying to update this cache line again and again, right? So essentially, this is how you implement acquire, and internally this exchange function is implemented with an exchange instruction, and to make it atomic, because in reality exchange is a load, and a store, right? So those may not be atomic because as you loaded the cache line, and maybe meanwhile someone says, okay, request for ownership message, and essentially the cache line got transferred here, was updated here, was a write, and then you try to do a store, you get the request for ownership to get the cache line back, right? But it may not have the same old value here, and instead you will receive the cache line with this new value, which another core updated, right? And so to make it atomic, you have to use this lock prefix, which explicitly says, okay, if I say lock here, if I receive a request for ownership in between the load the store here or some operation on the cache line, I will wait for I will not acknowledge it until I'm like done with this instruction, right? So this is clear, right? By the way, feel free to interrupt me at any time, right? Because and ask questions live. That's totally fine. Any questions right now? Okay, good. So and then okay, we said okay, like is it like the question which we had last time, and this is where we stopped, is essentially okay, is it okay to use those locks on a large like by 10 years ago standards uh, system, right? And it's still pretty large. 48 cores is decent today. It's not like large, but it's decent, right? So you can buy a server with 64 cores, maybe it was 128 cores, right? Today. That's totally fine. And the question is the following. So there's this paper which I assigned and you read it, which is called Non-Scalable Locks Are Dangerous. And the paper makes the following observation. So they run this email client exim, right? And it does scale. So like going from one core to 4 to 8, the performance goes up. So the throughput in messages processed per second goes up. And then suddenly at around, I don't know, maybe like 41 or 42 cores, it suddenly collapses, right? And instead of like hanging out here, maybe slowing down the performance growth, it literally collapses, right? And it's not okay because you suddenly say, look, like at least I expected it, expected it to stay somewhere over here in this performance range, but it really like goes down. And the question is why? So the authors of the paper essentially they said, okay, it's not unique to this specific tool, but they ran a bunch of different benchmark applications on Linux, and they observed the same performance collapse. Sometimes it happens sooner, sometimes it maybe happens later, and pretty late here, but it always happens. And in none of the cases, it just slows down like we all expected. Like if you take a programming class, you say, okay, scalability, multi-cores, locking, but at least you say that we know that it will not be linear growth like this always, right? But we expect some kind of slowdown saturation, but we do not expect collapse. And this is essentially the question which this paper is asking. So why is that we're collapsing here? And okay, so what they did is that they ran opera file, right? And surprisingly, those results like those slides actually take from the authors, but I take them not from these slides for this specific paper, but from a follow-up, I think it's OSDI paper, which is called something like Scalability Techniques for Linux, right? Which explores the collection of techniques for how to make Linux more scalable. One would ask, okay, why are we not reading that paper? In practice, the answer is that I think it's a little bit more watery, so it's harder to extract useful results. So that's why let's just concentrate on this one, right? But I am you're welcome to read the other one and enjoy it. So it has a couple of interesting tricks. It's just that maybe the paper is not ideal. Okay, so what they do here is they say, look, we will study we will collect something what is called performance profile with an O profile tool. And in a normal case on this 40 cores, this is how the distribution looks like, you know, and top the function which takes the most amount of time is this radix3 lookup, which probably lookups a VMA, so virtual memory area, which we just covered in our class, right, last month. And that seems fine, right? What it does is just like, does some kind of a file system operation, right? But on 48 cores, surprisingly, this radix3 lookup is not the first function, but a second function. And instead, another function, lookup mount, lookup underscore MNT, takes the most amount of time, 34%, right? Okay, they look into this function and they say, look, really nothing is going on here. This is a hash table lookup to look up a mount in a file system path. So file system path can be like whatever, full bar. And Linux apparently maintains a hash table and returns the amount point for this file system, right? And this hash table lookup, well, the hash table, Linux doesn't have millions of mounts, right? So it's like 10 to 15 mounts, maybe less, like maybe it's in the low, less than 10 most likely. So it theoretically should return within like 50 cycles, maybe. Like, agree with it? So because hash table fits in maybe in cache, maybe in a second level cache, something like that, right? But really, it should be a fast operation. The question is like, why is this like short function with a very short critical section? And again, any programming class will tell you, okay, guys, yeah, we get it. So we wanna write programs with short critical sections to maximize parallelism, because obviously maybe some other threads like T2 and T3 are trying to do the same operation. So they're spinning on this spin lock, trying to acquire the lock and to essentially uh, get something from this hash table. By the way, I'll ask you a question. So why do you think we need this spin lock to begin with? Why do we need it? Can someone tell me? Like, why are we protecting a hash table with a spin lock? Since I cannot see you, I'll just really quickly. Okay, we have George. George, why do we need to protect this hash table with a spin lock?
We protect it just in case the data has been changed by other cores. It might not even be there anymore.
Correct. And really, to answer this question, you have to ask yourself a question: can we implement a concurrent hash table? And one can say, okay, how do we build a hash table to begin with? And it can be something like an array where you store the keys, and if you're like hashing a key to a position in this array, maybe you have multiple collisions, so maybe you have a pointer here which leads you to and a linked list of values, something like this, right? And you say, look, I don't really know which value is mine, because like I have, this is maybe like 64 entries, right? And I have a large, the key space large, maybe collisions are frequent, and so you have to walk through the linked list to identify your value, right? And the question is like, what if someone concurrently, as you're doing this get and walking this list, maybe removes it and like updates this v1 to point to v3, something along those lines, right? And you are like in between transitioning with those pointers, like the question is like, is this operation correct or not? Most likely not, because you might maybe like everything is deleted. You look in at this element and this gets deleted, but maybe this one gets deleted as well. And then this pointer, for example, is a dangling pointer uh, pointing to nowhere, right? Agree with this? That's just one scenario how it can happen, right? One of you may say, okay, well, by the way, guys, I did very well at the computer science program at the University of Utah, so I actually know how to build a concurrent hash table, meaning that you might have a way to say, look, I actually can make sure that the hash table provide an atomic interface for hash and get operate for insertions and lookups, right? And it's doable, and in fact it's a lot of fun, and we should actually maybe take a look at it at some point, right? So if I ask the question, does anyone know how to build a concurrent hash table? The one which will be correct in face of concurrent deletions, for example, or insertions. Insertion will probably like add another element here, for example, and do not require spin lock. Do we know how to do it? Anyone? I probably take it as a no, but we might we might look. So essentially, concurrent hash tables are fun, but okay. So we need to protect them with a spin lock, right? Like this implementation, which we naively wrote, right? Like you and I programming the Linux kernel, for example, right? Okay, cool. So then we say, well, yeah, what's the problem? And in Linux, the spin lock which Linux implements is slightly different from the one which I was discussing above. Spin lock is implemented as two variables, the current and the next ticket, and we acquire the lock by essentially invoking an atomic fetch and increment operation on the next ticket, right? So essentially, initially ticket might be 0, the next ticket is 0. When you say, wow, fetch an increment, you get back 0, but increment the value of the ticket lock to 1, right? The next person says, okay, yeah, sure, I'm getting 1, and this is like thread 1, we like getting 1, thread 2 getting 1, thread 3 will get 2, for example, right? And the way it works is that when the spin lock is unlocked, the current ticket is incremented, right? And so essentially this, if this is the next, the current again starts with 0. And for T1, when it did this fetch and increment, it compared the value which is got, right? And it says, okay, if mine equals, I can go ahead forward, right? And it immediately exits this while loop. However, T1, which maybe did the acquisition right after T2, which did acquisition right after T1, will get to 1. It does the same operation, but the current value of the ticket lock is still 0, right? So this T2 will be essentially waiting on this T0 to change to 1, right? And it will change to 1 when the first thread essentially increments it here, right? We understand how it works, right? Any questions about it? And the reason for such implementation is that this atomic fetch and increment ensures some fairness, right? Because in our original exchange lock, where you're saying I have a lock and I trying to write 1 into it, and I'm reading I'm reading the value back. What if you will be starving? Like, what if the CPU, for whatever reason, your CPU on which you're running, like maybe CPU number 27, is somehow penalized and it never gets to win this game of exchange with other CPUs, right? For whatever reason, right? And then that's my understanding at least. And then you might like starve for longer than necessary. And apparently CPUs, like in whatever mechanism they're using, this mechanism of atomic fetch and increment is fair, meaning that if you arrive and try to increment, you will increment it before other threads who arrived after you, right? So which means that you kind of reserve the position. You reserve a position in a spin lock, so which means that you can like you will be waiting for other to unlock it, but for other to finish critical sections. But at least you got your spot, right? So it's a ticket lock. You got your ticket in like DMV office, and you're guaranteed to eventually get a turn, right? Okay, cool. So this is how Linux implements a spin lock. And now the question is like, why is it slow, right? So the way it works is that here we have a diagram of those 40. It's a 48 core machine, right? So we have a lock function, right, which is, let's assume, like is currently invoked in this core, and the cache line, which contains those two variables, the current ticket and the next ticket, is located on this core, right? So, and if you want to essentially increment the current value, unlocking the cache line is not on a figure, but it will be marked as blue, right? So what happens here in a like when you try to update essentially um, when you try to increment the next ticket, this cache line will flow to this cache core to this core, right? And it will be here because like I was saying, you do this request for ownership, essentially it goes to like last level cache. Maybe it's, if I understand correctly, the directory can be sitting here, but essentially it will say, okay, you own the cache line, so invalidate it, and then the directory will reply you back with the cache line, right? Okay, at this point, so this is the request for ownership. You're trying to acquire the lock. You got the cache line in the exclusive state here. Here it's in an invalid state, and you do this atomic increment on the cache line, right? So essentially incrementing the next ticket atomically. That's fine. That's how the cache line is behaving. At this point, meanwhile, and okay, this operation on this specific machine, and those numbers, remember I was quoting in my diagram about the Intel Sandy Bridge machine, right? I was quoting something roughly 250 cycles to get a cache line from a remote cache because you're traversing this cross-socket links, which on Intel are called UPI links. UPI stands for Unified Processor Interconnect. Before that, it was called UPI. I think it was, or it was Quick Path Interconnect, and now it's Unified Path Interconnect. It doesn't matter. It's a cross-socket link. It's just like giving you those three letters so you kind of remember when someone says it next time. You hopefully will just will ring a bell and you say, okay, yeah, I got it. So it's a cross-socket link, right? So the MIT paper, they quote a number from 120 if it's like on a neighboring core to 420 if you maybe have to traverse multiple links to reach, for example, this CPU, right? That happens, and this is probably a realistic topology of that AMD machine which they were using in that paper, right? Okay, so we updated now, like later on when we release the spin lock, we will update this cache line because it contains the same current ticket, right? Now, what's going on in a steady state, right? So, like all the cores essentially just they did this atomic increment, right? But then what's happening? They're sitting and waiting for this current ticket because this guy is implementing like a critical section. It will take some time. And at this point, they are essentially saying, okay, they're sitting in this line of code which implements this while loop, which is like a couple of instructions with a jump back. Essentially, it compares the value obtained from the increment with the current value of the ticket lock, right? And okay, so what's going on is that they're essentially like all of these guys have a cache line in a shared state on their caches, right? And they're like spinning in this cache line in this while loop, uh, just waiting for this value to change. When we do release here, spin unlock, we obviously need this cache line in the exclusive state because we want to write it, right? So the way we do it is that we send again this request for ownership. And in this case, this is remember I said that the home agent for this cache line is this core. So you communicate saying, okay, I want a request for ownership. It traverses the cache coherence protocol, reaches the directory, which essentially the way it works is that each cache line, I think, has a home, right? And the protocol knows where the home is. So the different cache lines will have different homes. So it's just to make sure that it's decentralized system. And essentially, when you send this request for ownership, the agent on the last level cache sends a broadcast message saying, okay, please invalidate your copies because someone requested this line in the exclusive state. So you have to essentially make sure that you don't have anything in your cache line. So all of them are transitioning into the invalid state, right? This is clear? By the way, like the last 5 slides, the paper just has 5 lines. So you have to read between the lines to understand what's going on. But the authors gave a talk at some point. So those are their slides. Okay, so at this point, we don't have the value of a ticket, right? And they say, because it was all invalidated, here it was updated, maybe it's sitting here in the exclusive state. But obviously, since they continue executed this while statement, they want to read it again because they load it from the trying to load from a private L1 cache. L1 cache says, okay, well, I don't have the cache line. What happens is that all of these cores issue a request. Let's for simplicity imagine that they want a cache line in a shared state, all of them, right? Because they all wanna read it, right? And I'm drawing this one again because I assume that it executes this critical section in a loop, like maybe a loop of a larger program. Maybe it's a next like if it execute this exim, then it arrives to the next message and it again drop back in a system call and it tries to do this mount lookup and it just like does it again, right? Although it just exited it, right? But in the time of this protocol, the rest of the execution is not significant. Even if it does something like 10,000 cycles, you will see that it's relatively short period for the rest of it. But those guys are just immediately getting the read of this cat line, trying to get it in a shared state, right? The real problem here is that, and this is what the paper says, is that uh, on most modern architectures, and this is how they phrase it, and I believe them, this read operation is serializing, meaning that all these individual reads will arrive as messages from different cores. Maybe this one from core 0, this is a message from core 67, this is a message from core 48. Maybe we didn't have 67, sorry. So let's assume 47 is the max probably. So this may be core 43, right? And so all of these messages are arriving to this directory agent, right? One after another, and they're kind of linearized in some kind of a queue, right? Agree with this? That's probably how it works, and this is what the authors are claiming. I don't know the micro architectural details, but their analysis seems plausible, right? If you're sitting in this queue, like like what's your average time of waiting in a queue? What is it proportional to? What's the bound? Is it O1, ON, or log n maybe? Can someone tell me? Did you guys read the paper? It also has a line. Anyone? Let's ask Jared, because Jared he has to know. He read the paper, he told me last
I
time.
read the paper about a week ago. I guess if you have a queue, you'd be oven, but
It's ON, but more specifically, you will most likely find yourself, like statistically speaking, in the middle of this queue, right? Sometimes
right.
you will be in the front, sometimes it will be in the back. Not that I'm very good at stats or analysis, but they say it's ON by half, right? So which is
Okay.
ON, but just like they're slightly more specific. Okay, but you got the point, right? That's why you say it's ON. So you will be waiting in this queue, like even if it's half of the time, it's still N by 2. And okay, sure, if our number was originally 120 to 420, then even if you multiply by n by 2, and n here is 48, and this is quickly scales up. So even if it's 100 cycles, it's 4,000 cycles right away. If it's 400 cycles, it's 16 uh, something. So it's 1600, 160, 100 cycles, right? So that's a pretty big number. Remember, I was saying that this call might take like 2,000 cycles, but you're waiting in this queue for 16,000 cycles, which is high, right? So essentially, you find yourself, even if you don't do anything and just simply acquiring and releasing clocks, and you do like a very short critical section, majority of your time you're just spending in this queue, right? And you may ask a question, okay, what's going on? Like, why is this a read? Because remember, I said, okay, those reads are arriving. Can we like discharge those reads asynchronously without waiting? Like, why is it really 120 cycles? Maybe it's like 50 cycles or something, some small number of cycles, because like you don't have to a full cycle when you do a read. You don't have to wait for the message to reach the requester, right? So this detail, I don't really know. I don't know why this constant stays so high, right? So maybe in modern architectures, it's really lower. And maybe this read operation is still something like even 20 cycles, right? And you say, look, does it solve the problem? Well, not really. It makes it better. Maybe it solves it in 64 cores because it's like 20 multiplied by 64, so roughly 128. It's still 1,000 cycles, so it's not like super fast. So it's a little bad, right? But if this number of cores goes from 64 to 128, you cannot really escape this O n by half, really. So you cannot set it with some kind of low constant, but really you will sooner or later hit a high constant again, right? So that's why even if you don't believe in this number, like I don't really, like for example, it seems a little too high to me, but sooner or later with larger number, of course, you will still hit the same problem, right? Uh, okay, that's kind of sucks. So probably, do you have a question, Josh, or whoever enabled the camera? No, you can talk. No, okay, just accidentally. Sorry. Uh, fine. So, but did you guys get the question? Get the problem?
Yeah.
So, and that's a little bit of a bummer. So, no matter how hard you try with your fine-grained critical sections, if you have a lock like this, you will see the same kind of collapse on any program. And as I was saying, like the beauty of this paper, in a way, I mean, it's a simple, interesting engineering fact. That's the beauty. But another layer of beauty is this use of those Markov's model, which says, okay, look, there's a mathematical model, and you can actually put different constants and plug 120, or if you like, you can plug 20, and then see, and the model reliably predicts what the real physical system is doing. So essentially, they plug the length of the critical section, length of the execution outside of the critical section, right? And this constant, how long it takes to like do the read, for example, and number of cores, right? And it still reliably predicts the behavior of a real system. It's pretty funny, right? So it's pretty impressive. Then you say you have kind of a reliable prediction of how the system will behave when this constant is 20. Okay, so cool. That's very important to understand that this is works like this, right? Because I don't know if anyone talks about it in any other classes, but okay, here we are. Now the question, right? What can we do about, right? And just if you don't believe me, like, and this is a diagram from a different source, and I can quote this source as well, which is probably useful. It's a time in nanoseconds per one atomic increment. So remember this: atomic, roughly speaking, a log plus an ink instruction on a variable, right? And people measure it, and originally it takes like in a matter of like 5 cycles, maybe even less, because of this log prefix. It takes a little bit of time. Like it's not like 2 cycles, which you would expect, that your access to the when you typically increment a variable in memory, so it roughly takes you 2 to 3 cycles, right? Because you're accessing a first level cache, right? But with the log prefix, it's a little slower, but not much. Maybe let's say 7 to 10 cycles, right? But it quickly like escalates. So, and the reason is very similar. So it's the same kind of idea that you will be serialized on accessing this cache line. So the moment you're trying to access a single cache line from multiple cores, your scaling story goes to hell, and it goes pretty like it's again 2,000 cycles, 2,400 cycles to do an atomic increment on 64 cores, right? So it's pretty impressive, right? So it's pretty slow, right? So it's not just the spin locks. If you're knowledgeable and you know what lock-free synchronization is, and atomic increment is a very kind of toy example of this lock-free synchronization, right? So you're not acquiring a lock around a variable which you're incrementing with this plus plus operation. Instead, you just simply like say, okay, I will be using this atomic increment lock with an increment instruction. But any other flavors of those algorithms, the moment you find yourself hitting the same cache line across multiple cores, you will see the same scalability problem. Of course, log free, if you say, look, and I mean, I don't know if it's clear. Let me just, if you have a large array, for example, like a hash table, for example, we are thinking about building a concurrent hash table. And let's imagine this array is something like, I don't know, 128 megabytes, right? And when you inserting in a hash table, you're doing some kind of an atomic exchange operation on one element of this array, right? So it will, if I ask you a question, how long it will take you? How many cycles? Like imagine it, there is some kind of a flag and it's set to 0 when the element is available. And you're doing an exchange operation trying to set 1, saying that this element is no longer available, we inserting a new value, right? And maybe you can insert the flag, the key, and the value in a single cache line with a single exchange instruction or something along those lines. Like I'm not really explaining. It's very close to how one flavor of a concurrent hash table can be constructed, right? But it's not a full kind of implementation of a hash table. But you can kind of believe that we are not too far from like building this hash table, because you say my hash function, I take a key, key returns me a pointer, I check if this flag is set, if it's already taken, and if it's an insertion, for example, you do some kind of a linear probing, you try the next element, check if this one is taken. If it's already taken, then check the next one, linear probing, right? And like on average, this chain is not very long, as long as your hash table is not fully utilized, right? And you find an empty element and you can insert in there, right? Agree? So that this is plausible way of building a concurrent hash table. But what I'm asking you is, I'm asking you to tell me how long it will take you. So, like here, I'm not acquiring any locks. I'm exchanging something. I'm exchanging a value in memory with another value, right? So if I ask you a question, how long this exchange operation will take? What will be the answer?
If you're so you're just asking how long it takes to
Mm-hmm,
pretty much send a read and then write to that same place of memory. So just two
mm-hmm.
memory accesses. It'd take a couple hundred cycles if there's nothing pending in the queue.
Meaning, what do you mean pending in a queue?
Well, because the memory controller also has a queue. So if there's not a lot of other memory requests happening, then it could happen pretty fast within 100 cycles or so. But then you also run into that kind of like that O(n) divided by 2 problem if there's a lot of memory requests to the same queue. But yeah, a couple hundred cycles.
Correct. And actually, this is a great answer. And I'll just like point out one additional thing. So if we have a uniform distribution of accesses to this hash table, right? Imagine we would have like 64 cores. I said that this is 128 megabytes of memory, right? So we have a ton of different elements. Um, and this ton of different elements, you typically get accesses to like uniformly from 64 cores. So you rarely conflict, right? Which means that your queue of O(n) by 2, in this case, n is roughly 1, right? Because no one else is trying to access it, right? And so what we're seeing here, if the accesses are uniform, then everything is fine, no contention, right? So lock-free really works because we're not touching a single cache line anywhere, right? We're touching different cache lines, one cache line, another cache line here, another cache line here. So everything is beautiful, right? However, if you suddenly have a different distribution of key accesses and you say, look, maybe 90% of my accesses to the hash table only access at 10% of keys, right? Like it's a different distribution, for example, right? So with whatever, like essentially, like one key gets accessed like a million times, the second key gets accessed like 500,000 times, the third one, the fourth, and the rest are almost never accessed, right? Just maybe it's a hash table which has information about some celebrities, right? And only those celebrities are frequently looked up. No one else is in the game, right? Because Anton is no one cares about Anton. I have like 7 accesses per week on LinkedIn, right? Or something like that. So like no one conflicts for me, right? But for those keys for which the accesses are conflicting, effectively your data, like your data set goes from 128 to this 10% of keys. So it's right roughly 12 megabytes. And at this point, you might start conflicting on the same cache lines. I mean, you will. Like it's just a question of the size of the hash table, the frequency of accesses, and the skew, right? And so at some point you will see this n, right? What I'm trying to explain here is that you cannot just like say, well, log 3 is bad because you will still hit this n divided by 2 problems. Unless you have contention, you will be just fine, right? It's beautiful here because without contention, like you said, the axis will have like roughly 200 cycles because that's how long it takes you to read the cache line, which may be sitting in another cache or in memory, right? But as long as contention goes up, then you have to start thinking, am I conflicting on the same cache lines? Am I still with this n equal to 1? Or maybe it's already like 16, or maybe it's 64. And the moment you are like greater than small number, you have a problem, right? But again, like what I'm saying is that that's the game of multiple things here, right? Did you get what I was trying to explain? Or are there any questions? Everyone is clear? So anyway, the point here is that if you're accessing different cache lines, you're fine. N is 1, life is beautiful. But in case of a spin lock, you're accessing the same cache line. In case of atomic increment, you're accessing the same cache line. Now I'll ask you a question. So can we solve it? Is it possible to figure out a solution to this problem of acquiring a lock around the hash table and releasing it? And if yes, then how? Any ideas? You should have ideas if you read the second paper.
I think you kind of spoiled it last time when we talked after class. Something about, I don't remember exactly. You had like an acronym, but
Mhm.
um,
RCU,
RCU,
read copy
yes.
update.
Yep.
Right. So I'll cover today two things. One way of how to even avoid acquiring this expensive synchronization primitive, and second is how to build it fast. And a third way, actually, I will also remember that the title of the first paper is Non-Scalable Locks Are Dangerous. But clearly, the scalable locks, first, clearly they do exist. Second, they are nice. They are not dangerous, right? So we have to figure out how to build a scalable lock, right? Okay, cool. So first, very simple engineering trick. You say, hold on, like this mount table, which we're looking up here, is rarely modified because it's only when you mount and unmount a directory, right? In most cases, you don't do it. You mount once per lifetime when you boot a system or plug some device, right? And you make the following observation. What if we have a per core hash tables, which locally cache the mounts? Then you say, look, if I first look up in a per core table and find the mount, I can return immediately without acquiring any lock, right? Agree with this? And my slow pass will be, okay, I'm not in a hash table in a local, it's not cached locally. I will acquire a spin lock, go to the global hash table, get the mount, release the spin lock, and then insert the mount into the local hash table. Kind of a beautiful engineering technique. You say, look, majority of my accesses can be served locally, and I will have a fast pass here, and my slow pass will be executed very, very occasionally, right? You might ask a question, okay, what happens if like when we do an insertion in this global hash table, right? Because clearly then local and the global ones diverged, right? So maybe we deleted an element, right? So how do we do this then? How can we synchronize in this case? Any ideas? Anyone does parallel programming? Really should have ideas. Where's my friend Zafang? Zafang, do you have an idea?
We
How
can
can we
have a
synchronize?
linked list.
You can have a linked list of what?
It's kind of like a ticket log, so you can add yourself to the tail of the linked list.
No, no, hold on. My problem is that like lookup works fine, but what if some other core inserts into the hash table? Then the per core mounts are not synchronized with the global hash table view, and we shouldn't go to
Ah,
the
okay.
local. So how can we? And I'm not acquiring, seemingly I'm not acquiring any locks around this local hash table, right? So somehow I need to signal the fact that, okay, look, this local copy is no longer valid, right? And that's kind of my answer. So I'm saying, look, like we probably can come up with a quick way to invalidate local copies of the hash tables, maybe atomically with respect to this read. And then everything will work, right? Right. And we can invalidate in a different manner. So we can, for example, uh, maybe even have some kind of a flag. It can be even a global variable, kind of like valid or invalid or something along this way, or version, right? And every time that you do a write into a global hash table, you like increment this version and you say, look, if my local version doesn't match the global version, it means that the global hash table diverged, and I have to like completely drop my local version, for example, and then repopulate it again. But it's okay because it's a rare operation, right? And since these versions is just like a single variable, we can do it atomically, right? So, and typically it's in a shared state on your core. So every time you do through your fast, you just read this variable and everything is fine, right? Does it make sense?
Yeah.
And
A
it's just
single
one
key
way to do
list.
it. And but probably there are better ways to do it, right? So do we agree that this approach works in this specific case, like with this local copy, right? Again, we made an observation that writes to the hash table are very, very infrequent. And so we don't have to acquire a lock to do a read, because typically just our local copy is just good enough. And the hash table is small enough so you can maintain multiple local copies without degrading your memory footprint. Agree with this? Take it as a yes for now. Okay, so that's solution number one. So that's essentially explanation of how it works, but I already explained. So kind of cute engineering trick, right? Okay, that's one way. And they provide, that's from this paper, Linux scalability techniques. They say that, okay, this is your scalability, this blue line, it just maybe slightly slower than like, no, it's actually faster even here. And then it continues to scale, right? That's pretty cool, right? So we avoid this collapse. That's technique number one. Okay, sometimes you can restructure your code to make sure that you avoid the scalability bottleneck. And that's the trick which they do here. Now my second trick. My second trick is how to build this scalable spin lock. Like, do we have an insight? I didn't assign any reading about it, but maybe you've heard of it. It's Michael, someone MCS, and Scott Lock. I think it's three people who invented the lock. Let me ask differently. Like the core of the problem with the non-scalable lock is that everyone is trying to spin on a single cache line. The question is it possible to build a lock in which you don't have to spin, or the people, like cores which try to acquire the lock, don't have to spin on the same cache line? Kind of, they will be spinning on different cache lines. Do we have a guess for how this can be done? And because now, if everyone spins on their own cache line, you're back into n equals to 1, right? Or maybe 2, if it's like the one who releases the lock and the core which releases the lock and the core which acquires it, right? But still very small constant. Any ideas for how to build the lock which, instead of spinning on a one single cache line, can spin on multiple different cache lines?
Um, my first guess that's probably wrong would be you have a single thread that distributes the same cache line to multiple cache lines, and then each thread can read their cache line, and then you have like a main thread that that updates all the cache lines. That's just a random guess, though. I
Actually,
don't actually know how
it's
to.
no, it's actually works this way. It's one way to structure synchronization. So altogether, you might want to like I forgot exactly how this pattern is. I think it's called something active, and I have to read on it. But I used to remember well. But in practice, you can actually synchronize without critical sections altogether. But instead, you say, look, I will be sending messages to all threads will be sending messages to a single dedicated server thread, and this server thread will somehow synchronize. It will receive messages. Maybe there will be multiple queues. Queues can be actually lockless, meaning that they don't have you don't need to have a synchronization primitive. But even if it's a synchronization primitive, it will be like on a cache line which connects a pair of threads, right? And this thread can maybe like fetch the messages which are arriving in those queues in some kind of a round robin manner, right? Saying, okay, I will take one from here, next one from here, next one from here. And like you say, they say you send a message to a thread and say, can I have a lock? And the thread, yes, later on replies to you when it fetches you from your queue, and it replies back to you, yes, you have it. And this is the synchronization section. That's exactly what you described. You say everyone else is waiting because they are waiting for the reply. And when this guy is done, it says unlock and sends a message, right? So that works, right? So we actually separated the locks, the cache lines from the lock, because it's a cache line which is like only per queue. Jerry, did you get the answer? So I think it was you who were saying, who suggested
Yeah,
this technique. So it actually works. Do you agree with this? So your technique works.
cool.
And does everyone else understand that it works? I mean, I was very far probably, right? The problem here is, of course, it's a little, I mean, first of all, it does work and it was tried in practice. And I think the debate is still out there whether this technique, man, there's a great paper, I now remember. Uh, we can talk about it. We can come back and talk. Uh, it's pretty amazing that this technique can actually be practical in many different scenarios. It somehow never is never on the radar. And that's why I'm saying that maybe we're still as a community are not agreeing whether this technique is in what kind of landscape it's beneficial to critical section. And there occasionally there is a paper which says, look, you guys are underestimating those, I think it's called active messages or something along those lines. And they can be very, very helpful, right? So that's one way to build it. However, there's another way to build it. That's the way which I will kind of like explain now. If we can structure a lock as a queue, so essentially when you try to acquire a lock, like instead of like trying to update a cache line and wait on it, you update the cache line once and you add yourself to that queue, saying, okay, now I'm the next in line. And then the next thread comes, says that read this pointer, says that there was someone in line, so I will be the next in line, but I will remember who will be in front of me, or vice versa. Maybe I will let the person in front of me to know that I'm waiting, which means that if this guy gets the lock first, instead of like spinning on this global cache line, I will be spinning maybe on his state or maybe on my state. And then he will update my state saying, okay, now the lock is free, and everyone will like essentially it's again, it's kind of like pairwise communication, right? So essentially, if there is a queue, then only the predecessor updates the successor, right? Saying, okay, the lock is yours. And the n is like 2, because one thread is spinning here and one thread will try to like essentially do the update, right? So if we can construct this queue, then the lock is scalable because they will never spin on the same cache line, right? They somehow atomically update this header, like the head of the lock, and maybe manage the queue somehow. Do you get the gist of this? The kind of the core idea that if you can construct this queue, then the lock will work. Okay, cool, Darren. Thank you. Okay, so let's do how it's like again. We're using here those. We're using this technique of lock-free programming. The reason I'm smiling because I got their names wrong. It's actually this guy. This guy is a Michael Scott, right? His first name is Michael and Scott, but M and C, this M in this lock comes not from his first name, but from the like these two letters in this other person's name, and so it's the two people who invented this lock, right? So okay, at a high level, they try to implement this queue, right? So it's a little bit maybe easier to understand from this example. So in an unlocked state, the lock has a queue and it's empty. It leads to nowhere. When the CPU comes in, it puts itself on the locks as the as kind of the next element, right? And its own next element, and this is the first CPU data structure, is empty right now. When the second CPU comes in and says, okay, I want to wait, I'll keep waiting on this lock. It again updates this pointer by pointing to itself, right? And right now you have this situation in which this pointer is dangling, this one is dangling, but essentially this guy will update this pointer, the next pointer of this guy, to point to the second CPU. And when this guy is done with the critical section, it essentially, it's not on the list anymore, but it will just use this pointer next to wake up this guy and say, okay, look, you are next. And now the queue will look like that, right? So let's see how it works. So when you do the in queue, so what there are essentially two cases here. So you say, look, I will try to access the global V variable with an exchange operation. And I will try to insert myself, right? So trying to, like, if this was the global lock, which is this LV variable, sorry, this is V. You try to essentially add yourself to this list, right? And you do it atomically. And there might be two cases. There might be a predecessor, meaning that someone was already sitting on this queue, right? And then you will get this pointer back. But if multiple threads simultaneously try to acquire a lock, only one of them gets this pointer. The other one will get the my node pointer, right? Because one of them wins, right? And or there might be no predecessor, and this original pointer was pointing to nowhere, right? And so this is the case. So essentially, if there was a predecessor, if essentially there was nothing there, you're done. You essentially, like, you entering the critical section, you don't have to do anything else. If there was a predecessor, you say, look, someone was waiting on the lock before me. And so what you're gonna do is that you take this someone and you say that that someone's who was waiting here, right? His next will be pointing to me. Sorry, the way, man, there is no there is no control Z. Maybe there is control Z. Is there control Z? No control Z. Let me do this. Let me just quickly razor. Instead of this pointer, really what happens is that you are updating, since you're coming my node and there was someone already sitting, right? So you have this predecessor pointing. You take his next and point to yourself, right? Agree with this? And naturally, when this guy, since he will enter the critical section first, it will notify you with your cache line that you're next to go into the critical section. Do you get this inspiration? I will go through the release function in a second, right? Did we get the acquire function, at least at the high level? It's very simple. So just one atomic operation, exchange. Again, same as before. You're inserting yourself on a queue, which kind of gives you an idea that you can build first in, first out FIFO queue, right? Easily with this a queue which is like which is atomic in phase of concurrent accesses, right? So essentially, if you have a head, you can also always insert yourself into the head of the queue, right? And that's what going on here with this exchange, right? And if someone was there before you, then you say, look, you're saying, I will be waiting for this guy to release the lock, and I will be spinning here on my own locked field on this cache line, right? Because I know that this guy who was in front of me will when change this locked to unlocked, and then I will go into the critical section. Does it make sense? Anyone, any questions? All good? Okay, let's take a look at the unlock function. So unlock is similar. So essentially, when you unlock, you can check your own my node next pointer. And if you don't have anything in next, uh, what do you do? I was thinking it's simple. I used to understand it, not anymore. If next is not, if next is null, right? I will, then what you do, if next is null, so essentially it's just you sitting on the LV, it's just you, right? You say my next is null, right? I don't have to notify anyone, likely. You will do a compare exchange saying, okay, you will compare exchange is yet another operation. It says, okay, I will compare the value at this memory location with my node value. And if it's still my node value, I will put 0 there, which means that this pointer will get updated to null, right? However, maybe someone concurrently was inserting themselves into this queue, which means that, okay, this value can change. And the return value, you say, okay, wow, it's no longer true. It's not you anymore. Some other node is inserted. Then you say, look, I'm done. So I don't have to do anything because I know that whoever inserted, no, actually, if it's actually equals, if no one got inserted, I'm done. If, however, someone gets inserted, I will be waiting for my node next pointer, waiting for this other node which got inserted into the queue. It will update my pointer to point to them. My pointer can still be 0 meanwhile for a while, right? But essentially, I will wait for the fact that my next pointer is not 0, and at this point I will exit this loop and I will say my node next is locked to 0 because we know that this guy will be waiting on its own locked field. Does it make sense? So essentially, it kind of goes case by case what can happen and what can work concurrently, right? And you can ask a question, okay, are we sure that this algorithm is correct? Well, it's much harder to prove, right? So typically those MCS locks and other concurrent, any kind of algorithm which involves lock-free data structures is hard to prove. Essentially, like it takes a while to convince yourself that you did everything right because you have to reason about all possible interleavings, right, of acquire and release. Hence this kind of fancy line. And it says, okay, I know that someone got inserted into the queue, but maybe there is a window of time where my next pointer is not yet updated and I have to wait on it, right? But at a high level, at least, I'm not gonna ask you, okay, tell me how it works. I just want you to have an intuition. Like maybe we will have a very simple assignment to build something lock-free, just to make sure that we understand, but it shouldn't be very hard. Okay, any questions? Believable? Everyone believes, but no one gives me a thumbs up anymore. Everyone is like, oh, okay, thank you, Jared. You saved me. So why did we solve the, thank you, cool, Japan. So why did we solve the scalability technique, scalability problem, right? Like, remember, here we were spinning on a single cache line, and here we're spinning on just a pair of cache lines, right? So here we do exchange into this cache line, which is kind of global because if no contention, in case of no contention, it's just one cache line, but n is small, right? It's just one or two threads, right? Which are contending for this cache line in acquire and release function. If contention builds up, then in many cases, what you're doing is that everyone is essentially sitting on a different cache line, and this cache line is different for every pair of threads, right? And so essentially, this is where you remember this invalidate refetch game. So it doesn't happen here because only one node occasionally writes into this cache line, and the other updates are happening through this my node next and locked field, right? So that's kind of beautiful. So we kind of separated them in between different cache lines. The ugly case here is that the traditional lock takes only one argument, the lock itself. Here you need to also pass this Q node, which breaks the API. You have to, meaning that you have to allocate memory for this Q node. That's why it's not like widely adopted, I guess, because it's a little harder to like, because in case of a lock in C, you say, look, lock data structure one allocated somewhere, everything else is orthogonal allocated in some other memory. Now you have to think about where to allocate this Q node and pass it around. It's a per CPU data structure, not fun. So you have to deal with multiple things. But in case of a kernel, it's definitely doable and people like do, right? And okay, cool. So a couple of low-level details to make sure that we are never bouncing cache lines around, right? So maybe we're so dumb that we happen to allocate the Q node data structures in the same cache line. To avoid it, we essentially say, look, by the way, make sure that we are like aligned to 64 bytes, which is the size of a cache line on the Intel architecture, that it will solve us the problem. And we'll also align this one to 64 bytes to make sure that each of those sit in a different cache line, right? Okay, so that's pretty cool. And they have a plot in a paper. Essentially, turns out that this MCS lock is scaled reasonably well. So again, as we were predicting, it's kind of the scaling like gradually slows along this curve, but at least it does avoid the collapse, right? So that's pretty nice, right? So if we ever experience this collapse, then we know what to do. We just say we're gonna update our locks to MCS locks, and everything else will be fine, right? Okay, cool. So let me stop here for any questions. So we learned a couple of things. We said, okay, look, we can either avoid acquiring a lock on the hash lookup altogether. We will restructure our code, or what worse comes to worse, we'll use this scalable lock, which makes sure that we never conflict on the same cache line, right? And in between, I was trying to explain this story with a hash table and optimistic concurrency, meaning that if you really like don't have physical conflict on the same cache line, then this problem of n divided by 2 kind of disappears, right? And you're totally fine, right? You feel free to use your exchange or compare and swap operations, which and swap to implement your log-free algorithm on a large data set, and you will never conflict, right? Okay, agree with this? Yeah, okay, cool. But now I have to explain yet another primitive, which is kind of funky and most likely will run out of time, but it's called read copy update. Again, the primitive is impressively powerful because it handles the case when the majority of accesses are reads and you have infrequent writes, what I cannot spell right, very, very well. Okay, let's consider the following use case, which is coming from another ACM paper. Again, that's the one which had a plot on atomic increments, right? Imagine you have a linked list. They tell you a story that it happens in the zoo. That's why elements are animals, like cats and different snakes. Your goal here is to make sure that you want to remove this cat from a list, right? And again, we kind of like, it's similar to my story about the hash table, right? So you say, look, I really need a lock around it, right? Because if I don't have a lock and I'm removing a cat and someone like accessing this ball, then it might dereference this pointer, and maybe this pointer points to still to cat, but cat is already like deleted, stuff like that, right? How can we do it? So you can make the following observation, that you can probably come up with an primitive which atomically updates this pointer. It's a little funky, right? Like you say, look, isn't it just a pointer, right? So like, can you just do boa next equals to GNU? Can you? Is it atomic? And what does it mean to be atomic? But what if this next is kind of sitting in between two cache lines somehow? And for example, the property which you want to achieve, that whoever reads this pointer either reads the old value, the pointer to cat, or reads the new value, but never a torn value, which is like half from the new write and half from the other write, right? So again, I kind of challenge you to think about it, whether it's atomic or not. I think it's not atomic in all architectures. It might be atomic on Intel when the pointer is entirely within the cache line. I'm pretty sure that I don't think that Intel will. It's a good question whether they can guarantee this atomicity or not, but you can ensure this atomicity with the read and write barrier, meaning that whoever observes when they want to read this pointer, they will make sure that all the writes are done, right? Which means that even if you're writing like two cache lines, they both will be done, which means that they will observe a new pointer, right? Imagine we did it, right? We also want to make sure that whoever like accesses the cache, the list will go directly to this GNU, completely skipping the cat because we removed the cat from the list, right? Now we have a question. Imagine one thread which was sitting here and it has a pointer on cat. And maybe it's sitting there for a while. Maybe it's like cache the cat, cached, and like does something, and it will be doing it forever, right? For some amount of time. At what point we can guarantee that all the readers of cat are gone, meaning that no one has a pointer pointing into cat? Because at this point we say, look, we can send the cat to free and deallocate the memory, and it's safe, right? Because no one has a pointer into cat. Can we do it somehow? Do you have a trick? It's a little funky. It's almost impossible to guess. But since you read the paper, RCU, uh, did you read the paper? You read the paper, and I read the paper, and I unfortunately say that if you read the paper, it might not be entirely clear how it works. Do you agree with this? Because really, I'm using a different paper to present RCU, right? I'm not using that paper which I assigned, right? So the one which I assigned just talks about how RCU is suddenly became popular in the Linux kernel, but doesn't really like tell you how to build it. But okay, let's make the following interesting construction. So imagine we somehow have a primitive, which is called synchronized RCU, which has a power to claim that all readers which were looking at cat finish looking at cat. How can we do it? So, and that's kind of beautiful. Before reading the cat, imagine we have a primitive which says disable preemption. It can be just done with a local flag, which says on a specific CPU, it sets a flag, disable preemption, like in a global variable for the operating system, which means that even if operating system will receive a timer interrupt, like for example in x86, it will look at this flag and says, okay, this thread doesn't want to be preempted, right? So we're not going to preempt. I will say I'll acknowledge the timer interrupt, but instead of doing a context switch, I will keep this thread running, which means that even if the timer interrupt hit here, we will return to execution of this thread and continue running. And maybe we're like, this is where the pointer to the cat is used, right, for a while. And when we enable preemption again, we guarantee that the code is constructed in such a manner that we no longer will be looking at cat, right? Do you follow this argument? So I just said, okay, disable preemption. It's a per CPU flag. Only this core touches this flag, no other cores. On other cores, there will be another flag, right? So another variable local to another core, right? Enable preemption just resets this flag back. Now, how can we implement synchronized RCU? Our goal is to make sure that all the threads which got stuck here when we started maybe synchronized RCU exited this RCU critical section. This is how it's called, like disable preemption, or you can say RCU disable, RCU enable, right? So how can we answer this question? That no threads are stuck in between disable preemption, enable preemption. Any insights?
The paper says to wait till all the CPUs have context switched at least once.
Exactly, because if you observe a context switch, it means that you were outside of preemption, right? Which means that even if you started RCU and the thread was here, it maybe even entered the disable preemption. Maybe it's looking at cat. But the moment you have a signal that the context switch happened, right? So if it happened here before, the point is that it will, by our construction, it will be observing a new value of the pointer. But if it got the old value of the pointer of a cat, by the time we see a context switch, it means that the thread exited the RCU critical section because preemption happened, which means that enable preemption was invoked, right? Do you agree with this? Does it make sense? I mean, it's nice to actually understand this because it's kind of beautiful in a way, because this disable preemption is not a classical lock. It doesn't set a flag globally. It just says a flag per core, which avoids our ON scalability problem, right? It just O1 always. Do we buy this argument? Any questions about it? Like, okay, thumbs up if you understood it, thumbs down if you don't. I don't know if you can show thumbs down. Well, man, sorry, the anonymous polling failed. Man, majority of people understood it. That's pretty cool. Sorry, I don't see your eyes, so maybe you could have just waved and said, yes, we got it. Sorry, don't have to say. But this is kind of beautiful, right? So now we have this power to I'll just take 2 more minutes. So we know that by the time synchronized RCU finished and it's sole preemption on every core, no one is looking at cat. Whoever will be navigating our linked list will land on a GNU, right? Which is fine. We're fine with that. They might disagree on exactly where the cat was deallocated. So some of them at some point of time will be still looking at cat, and some new ones already will be looking at GNU, but that's fine. So there's like kind of like disagreement, and you can detect it if you like, as the paper says, but it's typically unnecessary, is not required. But by the time we're done with synchronized RCU, we know that there are no readers which are looking at cat, if it's safe to deallocate cat, right? So it gives us a very powerful primitive. So in a realistic scenario, so I have a couple of slides which like essentially explain how to like RCU read log. It's essentially disable preemption plus plus to make sure that we can do it recursively. RCU read and log minus minus, and synchronize RCU in this naive implementation to make sure that we observe the context switch. It says just run on CPU, meaning schedule myself on every CPU in the system, right? And it can be done even in x86 if you say, like, it's kind of like a thread affinity. You say, I want to be scheduled on this CPU, and even the schedulers in x86 who can match the the mask of your affinity and schedule you specifically only on that CPU on which you require. But Linux actually keeps track of those because it's much faster to just observe the context switches lazily versus like invoke and move the thread between CPUs, right? But it's kind of the same effect. Here I kind of explain how it can be built in Linux. But for example, in our example, what we can do here is that we, for example, can say how does it work? So it's essentially like invalidating the local mounts here. So we're synchronizing them with RCUs. So essentially, we can be looking at a local table, and then maybe a slightly better example. I wanted to. So for okay, let's come back here. So I wanted to, since it's like 4 minutes past the hour, I will provide examples of how RCUs can be used in practice, but in a way, what it gives you is that if you have a pointer to a data structure, like a hash table or a system call table, you say, look, typically you just read this table and you want to make sure that the reads are consistent. Then you want to say, I want to update this table. I want to write into it. What you're doing is that you're actually allocating a new copy of this table. Like you first copy everything what was here, then you do your write into this copy, right? And at this point, you say, look, at what point it's safe to deallocate the old table? Well, when you RCU synchronize, at this point, you know that no one is looking at this table, right? And so because everyone does this RCU lock, RCU unlock, and so this new version of a table can be in place, and it's kind of like versioning game. So we'll go through those examples next time, but kind of you will have an intuition. Okay, next Monday I will be back to Salt Lake City, so the lecture will be in person. I will likely assign a homework real soon. So make sure that you finish your previous homework, which I think is due today. And I'll see you then on Monday. Let me know if there are any questions. All good? Then sure, guys, I'll see you Monday. I'll stop sharing, stop the Zoom. Bye-bye.
Bye. Thank you.